Okay. So, welcome you all to take part in the fourth Gauge Gravity Talk of Season 2. This online seminar series focuses broadly on diverse topics in gauge gravity theories. And this talk will be recorded and we will be uploading it on the CHEP YouTube channel. So there is some instruction for the audience. So audience, they will be muted during the talk. Members can ask question by raising hands, and so they'll be communicated to the speaker by the moderator, and probably the speaker can also just check the chat box also from this thing. And but if there are urgent question, we can just definitely have a discussion right in the during the talk itself. Basically, if there's some important question, something is this thing, you can just clarify immediately. So today's speaker is Batoul Banihashemi. Is it right, Batoul?
Yes, Batoul, yes.
Yes. So she is from Stanford University. She did her PhD from Maryland under Ted Jacobson. Thereafter, she was a postdoc at UC Santa Cruz, and following which she joined Stanford in 2025. So today she will be talking to us about horizon thermodynamics from Lorentzian path integral. So Bataul, over to you.
Thank you very much, Gaurav, and thank you all for being here. Thanks for the invitation and the opportunity to speak in this seminar series. So this talk is based on the work that I've done during the past years with my PhD advisor, Ted Jacobson, some of which are discussed in these papers, and there's also some ongoing work. Please interrupt me during the talk if you have any questions, although I don't see the chat box while I'm presenting, so if somebody can tell me if there's a question in the chat, I appreciate it. Let me start by reviewing the groundbreaking work of Gibbons and Hawking, which is almost 50 years old now. In which they computed the horizon entropy by writing a path integral representation for the thermal partition function, just like a quantum field theory system, but now for a gravitational system. So this path integral is a sum over metrics and other fields, and the exponent here is the Euclidean action. And this formula was applied to both black hole horizons and also cosmological horizons. In the case of the black hole, the Euclidean section in 4 spacetime dimensions has the topology of a 2-disk cross S2. So this is the disk part, and on each point of the disk we have a 2-sphere. They also applied this formula to the case of the cosmological horizon in the Cedar space, and the Euclidean section of that space in 4 spacetime dimension is a 4-sphere. So they used these Euclidean geometries in order to obtain an approximation or an estimate for this object partition function, from which... Is there a question? No, okay. From which we can obtain the entropy by the usual formula. Beta here is the inverse temperature. And what they found was indeed the famous result of area of the horizon over 4 in Planck's units. So this is, of course, a very valuable result that they found, area over 4G, which was matching the result that was found by other methods. And this is indeed a step towards understanding better the quantum aspects of gravitational systems that have horizons in particular. But first of all, this is an approximation. This is the leading order term. In the meantime, since this work, people have worked out one-loop corrections to this formula, and there has been various other developments around this subject. But something that is missing is like the first principle arguments that actually gives us this result. And to this day, it looks like that establishing the whole set of fundamental rules that govern the gravitational path integral, from which we can obtain thermodynamic results like the entropy for the gravitational system, are not known. So I'm gonna point out in the talk some of these challenges. Sorry, I hear some noise. I mean, I think I hear my own voice. Okay, now it's better. Thank you very much. Right, so I'm gonna point out to some of the challenges that we have to deal with in order to consider gravitational path integrals and describe some attempts to deal with some of these challenges that Ted and I have been thinking about. This path integral, especially in the Euclidean sector, has been a powerful tool and has provided wonderful insights into non-perturbative aspects of quantum gravity. It has been implemented in various cases, different types of horizons, different types of boundary conditions, obtaining thermodynamic results, phase transition, getting the entanglement entropy formula, quantum extremal surface formula, all that story, and also has been very useful and very crucial in recent developments in attempts to resolve the black hole information puzzle. In most of these cases, there is a Euclidean saddle point that gives us the approximation to the path integral, which has been written in the covariant form. By covariant form, I mean the path integral in the configuration space, and the integrand is usually written in terms of a covariant action for general relativity or some like higher order corrections to that. So let's see what this path integral is and what are the problems with this formula, or some of the problems. So here I'm just gonna argue that this Euclidean path integral, as written like this, is not actually a well-defined quantity. First of all, if the left-hand side is supposed to represent some thermal partition function, which is some trace over e to the minus beta h being the Hamiltonian of the system, and trace is over the states in the physical Hilbert space, there is no derivation or there is no connection, a rigorous connection between this formula and this Euclidean path integral formula. So it is not clear that whether one can go through a step-by-step derivation starting from this point and reaching to that point. And I will describe some of the actually challenges or issues that would prevent one to start from here and get to this formula. But maybe more famously, this Euclidean path integral suffers from the conformal mode problem. Conformal mode problem tells us that if we consider fluctuations around a saddle point, there are fluctuations that make the Euclidean action unbounded from below. That would mean the integrand here, which is e to the minus I being the Euclidean action, is divergent. So this quantity by itself is not a well-defined quantity. This issue was first identified by Gibbons, Hawking, and Perry, again, a very long time ago, and they themselves provided the remedy of rotating the contour for those problematic fluctuations such that basically a wrong Gaussian integral becomes convergent. This proposal might work in some cases, but it is kind of ad hoc and might not be satisfactory in the most general case. And also there are examples in which applying this method would give us some obscure phase factors. For example, in the sum over spheres, which is the discussion of computing the fluctuations on top of the Sitter space, which was done by Joe Bolshinsky in the 80s. And there are some unwanted phase factors, and there has been recent interest in the subject. People have worked out this phase factor, including an observer in the de Sitter space, or counting the modes in a different way. So this is an ongoing line of research. But one general lesson is this formula by itself has this problem. So this cannot be equivalent to some trace of e to the minus beta h. One comment about the conformal mode problem. So it was worked out by Hardell and Schleich and also other people after them, that if you focus on linearized gravity, they showed that if you only consider the modes in the path integral that satisfy the constraints of the general relativity theory, this conformal mode problem is removed. So the idea is that those fluctuations that would make the action unbounded below, they are not actually dynamical degrees of freedom. They are rather constrained by the constraint equations of GR. And as I was saying, this Euclidean path integral does not implement these constraint equations. So obviously it has this problem of the conformal mode. I also would like to mention this very recent work by Horowitz, Maroff, and Santos, in which they showed that if you go beyond the linearized level, they found solutions, not perturbative, but like non-perturbative solutions to the constraint equation that, although they satisfy the constraints, but they can still make the Euclidean action unbounded below. So this just shows that writing this formula again is problematic, even if you satisfy the constraints. The constraints are not enough to make this purely Euclidean functional integral a well-defined object. So let's see what happens in the case of gravity if we really start from this formula, trace of e to the minus beta h, which is our starting point. And if we really try to derive a path integral representation for this object. A very brief review of the simpler cases. Let's start with a quantum particle. If we start with this formula for a quantum particle, we end up with, we follow the usual procedure of obtaining the path integral. This is some evolution operator in Euclidean time. We can still discretize the time and insert complete sets of states at each instant of time. And what we end up with at the end of the day is a path integral over all paths that are periodic in this Euclidean time. And the exponent here is e to the minus Euclidean action, which is the sum of the kinetic and potential terms. So it's like an inverted potential problem. This can be easily generalized into the case of a field theory, in which instead of like some coordinates, we have a sum over fields that are periodic in the Euclidean time. What happens in the case of gravity is that there are multiple differences. First of all, this Hamiltonian here that we might want to start with is a boundary term, and that's because in general relativity there's this diffeomorphism invariance symmetry. So the Hamiltonian that generates time evolution, let's say for now, is a pure constraint term unless there is some boundary to the space-time. This boundary can be either at asymptotic infinity or at some finite boundary. So we have to deal with that. But maybe more crucially, time, so some time duration or some time loop, the length of which is identified with the inverse temperature, is a metric dependent quantity, and it depends on the loop on which this integral is measured. So it depends on which point in the bulk you are standing. So that would mean if you want to start with this formula, you have to pick presumably some boundary with some boundary conditions, and pick the boundary time loop to be your starting point in order to derive a path integral representation for this trace. And something that I'm gonna talk more about is this issue of identifying the integration contours for various field variables that arise in the path integral. So we have to tackle all these problems among other stuff. Now let's see if we follow our nose and write this trace for the gravitational system in which the Hamiltonian, as I was saying, is a sum of the constraints on a special slice sigma. This curly H represents the momentum and Hamiltonian constraint of GR. And if there is a boundary for a spacetime, there is also a boundary term in the Hamiltonian. This trace here is over the reduced Hilbert space and classically reduced phase space, which is the physical states that satisfy the constraints. We can still do the same thing that we did for let's say a quantum particle, discretize the time direction and insert complete sets of physical states at each time. And if we do that, we get a reduced phase space path integral. And that by phase space, I mean a path integral over induced geometries on each time slice and their conjugate momenta. And in the exponent, we get the usual e to the I pq dot term. So this is the usual pq dot term. And this term here comes from the boundary term in the Hamiltonian. So in this expression, I have omitted the gauge fixing terms because they're not going to play a role here. This delta function here, however, is important. This implies the constraints equation and makes sure that this is a phase space path integral over the reduced phase space. So the physical degrees of freedom. We can express this delta function in terms of its Fourier integral using some auxiliary fields lambda that are gonna be identified with the lapse and shift. So this is a functional Fourier integral over these fields. We substitute this delta function by e to the I lambda constraints. So remember that one attempt is to see how close we can get from this starting point, trace of e to the minus beta h, to the Euclidean path integral that is used very, very commonly. And next step towards that goal is to integrate out the momenta here, because that path integral that we discussed before was a configuration space path integral. But one thing to notice and observe immediately is that if we want to look at the stationary point of this path integral of this exponent, because there is this coefficient that appears with an I here and another terms that appear with real coefficients, the stationary point of this exponent has a pure imaginary lapse and shift. So that means if we want to go through that stationary point, so we pick a contour such that it goes through that stationary point, because eventually we want to approximate this path integral using the stationary point, we have to deform the integration contour of these auxiliary fields, lapse and shift, such that they go through that imaginary value at each point of a space-time. So this is a cartoon representing the same idea. Originally, the integration contour of these auxiliary fields was on the real line, and the reason is we wanted to impose the constraint. So we start by the real line contour, but in order to go through the stationary point, we need to deform this contour if we want to include that stationary point. So on that stationary point, and probably some nearby points in the field space, the integrand becomes e to the minus action for that Euclidean section. I'm saying Euclidean, it could be complex in general because of the shift vector, but I'm not being very precise distinguishing between Euclidean and complex. By imaginary lapse, I mean having a Euclidean signature metric in general. I mean, the shift vector does not play a crucial role in what I'm gonna discuss here. So the main point is that this is the closest that we can get to this Euclidean path integral expression that was written in order to find the partition function from which we can obtain the entropy. But strictly speaking, this Euclidean path integral is not equivalent to the partition function being trace of e to the minus beta h. We need non-Euclidean configurations, non-Euclidean or non-imaginary lapse and shift in order to maintain this equivalence and also make sure that we remain on the physical Hilbert space. So one big question is whether this contour deformation is justified and also whether it's possible in the most general cases. Let's look at this phase space path integral once more. So I showed you before this expression where we had some like mixed terms with imaginary and real coefficients. Now imagine we want to integrate out the momenta anyways. And by doing so, that's equivalent up to some field-dependent coefficients that sit next to this exponential. That's equivalent to setting this momenta equal to their values in terms of field derivatives. And this is kind of the reverse of the ADM decomposition. You can write the momenta in terms of the derivatives of the fields. And if you do so, this bulk integral turns into the usual Einstein-Hilbert term. Here I'm writing the positive cosmological constant term as well. This L is the de Sitter length. But the main point here is by doing so, you generate some boundary terms coming from this reverse ADM decomposition procedure I was talking about. You get some boundary terms with imaginary coefficients, and I also expanded this term with the real coefficient, which is the boundary term compatible with the Dirichlet condition that you have in the Hamiltonian. So immediately here you see that we need to deform the integration contour for these auxiliary fields, lapse and shift, in order to get rid of these boundary terms. So let's say this lambda is some minus I, some real functions. Then you can combine this term with this term and then write the whole thing as the Gibbons-Hawking York term that one adds to the Einstein-Hilbert bulk term in order to have a well-defined action for the gravitational system. And if you also deform the shift vector to be some minus I, some real function, you can cancel this term against this term. So the main point is this contour deformation at this level is motivated by like dealing with these mixed boundary terms. One can say, well, maybe you're not looking at the right quantity. Maybe you can still come up with some path integral that avoids this contour deformation. So one alternative to this derivation is to look at a different quantity, like a density of states, as I will explain right now. Another option is to look at the spacetimes that don't have any boundary at all, so you don't have to deal with these mixed terms. And that's where I will talk about the Sidereau space. So let's go through these alternative options to see whether we can totally avoid this contour deformation of the lapse shift. First case is, as I was saying, density of states. So this is something that Brown and York looked into in order to come up with some microcanonical path integral. But the starting point is writing the density of states at some energy E that can be written as a trace of the delta function that is peaked around that energy. H again is the Hamiltonian. You can write the delta function in terms of its Fourier integral. And now if you take the trace inside the integral, you end up with a trace of an operator that seemingly is like a time evolution with the real time. So apparently you can write this trace of e to the minus iht in the gravitational system in terms of a path integral with the integrand being e to the I times the Lorentzian action. So apparently the contour deformation that I was talking about before can be avoided here. And let's see what this computation gives us at the end if we try to estimate this density of states using the real-time path integral. The idea is to approximate this again to leading order by finding the stationary point of the whole exponent here. So we have this Lorentzian action here, but we also have this ET term in the exponent. So we need to find the stationary point of the whole thing here. If you look at the Brown and York paper, this is the equivalent of their microcanonical action. So this is the action that is compatible with fixing the energy at the boundary as opposed to temperature. So this is a real time, this looks like a real path integral. So what is the stationary point? Can we find a Lorentzian solution with which we can estimate this path integral? And having the problem of horizons in mind, the answer is, well, let's look at the region outside a horizon. It could be a black hole horizon or a cosmological horizon. And because we are dealing with a trace, if we pick two time slices that meet at the bifurcated surface, in order to come up with the right geometry, we have to identify the initial time with the final time. So this configuration was also extensively used in a recent work by Don Marolf, and we were also thinking about this in the context of density of states. So eventually what we get after the identification is some configuration like this. This is a geometry that is Lorentzian, that is almost a solution, almost a Lorentzian solution. I say almost because there is a Lorentzian conical singularity here, which we also called closed time-like curve singularity. That's because, remember, this loop here is a real-time loop. So that loop shrinks to zero size at the tip, which is the location of the horizon. But nevertheless, let's say we can estimate the path integral using this geometry. So the next task is to compute the action for this geometry. And the procedure for doing that is, one way is to kind of excise the near singularity region. The regular part of this geometry contributes a real value to the total action that we can compute easily. But now let's focus on the action for this singular part, which is shaded gray. The point is, if you get very close to the horizon, this geometry can be described by Rindler geometry, and this little cone here is actually a Rindler cone, so you can describe it with the usual Rindler coordinates. Where C here is the proper distance away from this horizon. So we have a cutoff at epsilon, and we are going to send it to 0 at the end in order to evaluate this action. How do we deal with this Lorentzian conical singularity? Well, we were very much inspired by the work of Luko and Sorkin. They have a very beautiful paper in the context of topology change in two-dimensional gravity. So imagine I rotate this little cone by 90 degrees, then this cone can represent a topology change from nothing to a sphere, right? So that was the context where Luko and Sorkin were interested in computing the action for this type of configurations, but we can implement their method exactly to this entropy computation as well, or density of states computation as well. So what they did was introducing a pure imaginary regulator into the metric. So if I write that in terms of the Rindler coordinates I was talking about before, that would mean I would need to add some extra terms in the action. I can compute the Ricci scalar for this regularized complex metric, and it picks up a delta function contribution from the tip of that Rindler cone that has a complex strength. Well, that's fine, because if I calculate the whole action combining with the regular part of the geometry and then take the zero limit of this regulator gamma, the total action becomes pure imaginary, which is good because in the exponent I had I times the action, so that would lead to a real value for the density of states and hence a real value for the entropy. You might have noticed that there is a sign ambiguity in picking the sign of this complex regulator, and Luko and Sorkin picked this sign in order for this complex metric to be allowable in order to make the integral of any fluctuations that one can put on this complex metric convergent. So this fluctuation convergence criterion was actually first mentioned by Halliwell and Hardell and was also used by Luko and Sorkin, and nowadays it's known as the Konsevi-Segal-Wheaton criterion. And I noticed that Gaurav also had a paper like yesterday which was related to this criterion. This is a criterion that might not be satisfied in all cases that are interesting in path integral for quantum gravitational systems. There are cases where this criterion is even more constrained, but nevertheless, if we pick that criterion, if we only allow metrics that respect that fluctuation convergence criterion, we indeed get the lower sign. I mean, that's what Luko and Sorkin argued, that we should pick the lower sign here, which of course gives us the expected entropy, which is the plus sign, so we get the area over 4G. This whole story just brings up the question of what type of action or what value of the action should we generally assign to this type of CTC singularities. So again, remember this is a Lorentzian time loop that shrinks to 0. Maybe we can use some analytically continued version of the Gauss-Bonnet formula. So the relevant geometry here is this just two-dimensional, that is a topological disk. And if we analytically continue the Gauss-Bonnet formula, instead of the usual like 2 pi times the Euler character, which is 1 for the disk, we get a factor of I here. This formula has been implemented in many recent works, including in obtaining replica wormholes using Lorentzian path integral, and also in the Regi calculus derivation for the entropy, and various other cases. But notice that there is again the same sign ambiguity that Luko and Sorkin was also discussed. Actually, they also have this formula in their paper, and they picked a sign that is compatible with the fluctuation convergence criterion. So again, if we use this formula, we get an imaginary part of the action that has a sign ambiguity and leads to this formula for the partition function. As far as I know, there is no first principle argument that can fix this sign for us. So maybe one possibility is going back to the original phase space path integral that is more fundamental and see whether that can fix this sign for us. I'm going to comment on the phase space path integral at the end. But for now, let me turn to the second important example, which is the case of a space-time with no boundary. Maybe the most important example is the de Sitter space example, in which at each global time slice we have a closed surface. So if we have a d plus one dimensional de Sitter space, each time slice represents a d-dimensional sphere. So already, because there is no boundary here, understanding thermodynamics of de Sitter space is a little bit obscure. So in one of our papers, we introduced a finite time-like boundary inside the static patch of de Sitter space in order to understand better the entropy derivation of the de Sitter space, and also understanding the first law of thermodynamics, again using this time-like boundary. This time-like boundary has been introduced in various cases, like for example in the TT bar deformation for holography, or like when people introduce an observer in the static patch. This is also relevant for those purposes. But eventually, we would like to send this boundary all the way to the pole of this sphere, which sits at r equals 0, in order to recover the entire static patch. And also because, remember, we wanted to get rid of those complex boundary terms in the action when we were deriving the path integral. So our goal is to first introduce a boundary, but then send it to 0. And upon sending the boundary to 0 size, the Euclidean saddle topology changes from a disk cross S2 to a 4 sphere. And the picture to have in mind is that during that process, this spatial slice sigma becomes a 3 ball. Let's say we are in 4 space-time dimensions. So this becomes a 3 ball. And we need to revolve it around the time circle, but the boundary of this 3 ball is the horizon. So the boundary needs to be kept fixed. And if we do that revolution in time with the fixed surface of the ball, we get a 4 sphere. Interestingly, during that limit, by doing that limit, if we start from trace of e to the minus beta h, now h here again is the boundary term that we defined on this boundary, and it's basically the Brown-York energy that you get, that you define on this boundary. If we do this process, do this limit, Because the Brown-York energy becomes zero at the end of that limiting process. So you get trace of e to the zero, or trace of the identity operator. So from this perspective, the entropy of the Sider space that is obtained from log of this object, log of this partition function, is actually the log of the dimension of the Hilbert space of all the states that were living on this ball and are surrounded by the horizon. So without the boundary, the object of interest is just trace of the identity operator that indicates the log of the dimension of the Hilbert space. So let's go back to the derivation. Let's see how far we can go in deriving a path integral representation for this trace. So again, this trace is over the reduced phase space path reduced phase space. I mean, it's over the physical Hilbert space. So when you turn it into the phase space path integral, it's over the reduced variables that satisfy the constraints. And since there is no h here, the only term that appears in the exponent is just the I p q dot term, where p and q are the constrained gauge fixed phase space variables. And notice that although there is a time integral here, but there's also q dot here. So this sum is actually a sum over all loops in the phase space with this weight, p dq. So this is an invariant. I think it's called Poincare invariant. How to implement this in the case of gravity? Again, we have the phase space path integral. Here I have written explicitly the gauge fixing term and the Faddeev-Popov determinant that you need because of this gauge fixing. And again, the delta function that imposes the constraint can be written in terms of the lapse and shift integral. And here we have the constraints. These functions, the auxiliary functions, originally are integrated on the entire real line to impose the constraint. And we can think that, oh, okay, maybe from here we can again integrate out the momenta in order to get the phase space path integral. But in order to get the configuration space path integral with some Lorentzian action in the exponent. But one important point is, once we do first the momentum integrals and keeping the lapse integral to the end, integrating out the momenta here, and remember that the Hamiltonian constraint is quadratic in momenta, but integrating out the momenta creates an essential singularity in the lapse function. Because remember, pi in general relativity is related to the extrinsic curvature, which is basically h dot over the lapse function. So integrating out the momenta means replacing h by its value in terms of field variables and their derivatives. So you get an essential singularity for the lapse. So that means you cannot simply interchange the order of integration of the lapse function and the momenta. Therefore, in order to insist on integrating out the momenta first, it looks like that the lapse contour deformation is inevitable. So remember, we went through all these Lorentzian path integral discussion in order to see whether we can avoid the complications of deformation of the integration contour. But in both cases, like either in deriving the expression for the density of states, in which it was written in terms of some real-time path integral, or also in deriving a path integral representation for the trace of the identity, it looks like that we have to integrate out the momentum first in order to get to the configuration space path integral. However, this creates an essential singularity in the lapse, so we cannot just simply interchange the order of the integrations. And because of this essential singularity, we have to first deform the integration contour of the lapse function such that once we integrate out the momenta, that integration is doable, or in other words, integration over the momenta is convergent. And in our paper with Ted, we discussed that we need to displace the lapse function integral from the real line to slightly below the real line into the complex plane. And we did that in a gauge where the total trace of this momentum is constant, which is usually called the constant mean curvature gauge. And at least in that gauge, this deformation is doable, and we worked out an illustrative example in which we explicitly showed that if we do this contour deformation in the lapse function, you can indeed interchange the order of the momentum integral with the lapse integral. And interestingly, this prescription is consistent with the fluctuation convergence criterion that I discussed before. And maybe this is a welcoming feature because introducing an imaginary term in the lapse actually opens up the possibility of having an imaginary part in the action. And having an imaginary part in the action is good because remember, now that we don't have the Euclidean path integral, we have e to the I times the Lorentzian action. And unless that Lorentzian action has some imaginary part, we cannot obtain the leading order term in the entropy, which is a real value like A over 4G. So the main lesson here is, in order to start from the trace and get to the path integral that we want in the configuration space, there has to be this deformation in the lapse contour. Yes, there's a question.
Batul, so I was just wondering, like this deformation of n by I epsilon, like, so is there a systematic way of choosing these deformations, or like we are just requiring that the deformation has to be chosen in such a way so that basically these issues of consistent definition of the integral can be done?
So one thing for sure is that we have to deform it away from the essential singularity at n equals 0. So that's one thing for sure we have to satisfy. Another criterion is that we need to make sure that the deformed contour still imposes the constraint. So if we start from the real line, maybe we need to deform it such that maybe the endpoints are fixed or held very close to the original endpoints of the integration. But apart from that, for example, if you're asking whether it's minus I epsilon or plus I epsilon, well, in that case that we considered, it had to be a minus I epsilon because we needed to create a deformed contour such that the momentum integrals become convergent after all. And had we chosen and remember, momentum integrals are important. I mean, momentum integrals can be done by looking at the constraints, which is quadratic in the momentum. And we found that if we pick the wrong sign here, those momentum integrals are not convergent. So at least we can say something about the sign of this I epsilon. But other than that, I don't know how to construct the deformed contour. I mean, I don't have any other prescription.
Ah, okay, okay, okay. I see.
But then this consistency with the convergence, fluctuation convergence criterion is something that we observed afterwards. Like we picked this deformed contour, and then we observed that, oh, by the way, this is also consistent with this criterion.
Isn't it possible, like, to use Picard-Lipschitz criteria to pick up the contour, which I don't know. Maybe there's a
Yeah,
saddle is
yeah.
there. Maybe one can go around, pass by through the saddles, basically.
Right. Yeah, this is a very interesting subject, and I saw that in the previous talks in this seminar series, people have discussed this point and this method a lot. So, as far as I understand, the Picard-Lipschitz method is to basically identify the right contour that goes through a stationary point or a saddle
Yes,
point.
yes.
Here, I'm not even there. I mean, I'm not even
Okay, I see.
looking at the saddle point. I'm just saying, just very formally, in order to
Okay,
go from this phase space to the configuration space and interchange the order of integration of lapse and momentum, we have to do this deformation,
I
let
see.
alone going through the saddle. Yeah.
Right,
This
right.
is even this is even a step
Yeah,
before
yeah, yeah,
that
yeah,
I'm
yeah.
saying. Yeah.
I see.
Yeah, thank you for the
Ah, okay,
question.
okay. Yeah. Thanks for it.
Yeah, so finally, let me just make some comments about the phase space path integral. So we've seen that coming up with this configuration space path integral has its own dramas, I would say. And also there was that sign ambiguity that one could hope can be fixed by going back to the phase space path integral. So we also tried to at least derive the leading order term in the entropy using a phase space path integral. And in that setup, the spatial slices that all end at the bifurcate horizon, they all have an inner boundary. So in the case where there is a like outer boundary, like for like black hole case, I'm not talking about that boundary. I'm talking about the boundary of the spatial slice that is basically the bifurcate horizon. And because we have that inner boundary, we need to add a term at that inner boundary to the Hamiltonian in order to make the variational problem of the Hamiltonian system well defined. And that boundary term turns out to be an integral over that inner boundary, which you can think of it as a bifurcate surface of the horizon, of the radial derivative of the lapse function on the boundary. So in order to have a well-defined variation problem, we need to fix the time integral of this quantity. We need to assign some value to the time integral of this quantity. Well, at that stationary point, everything vanishes besides the time integral of this contribution to the Hamiltonian. So the path integral becomes to the leading order this object, and if we want to compute the entropy, we get the exponent, which is minus I times this thing. And if we impose the condition where the time integral of this quantity here is some imaginary number, that would mean this radial derivative of the lapse should have some very specific value, which is imaginary, first of all, but also depending on the time duration that we have picked for the loop, for the time loop. And this by itself is not very satisfactory, because this condition is not a condition that you would impose on the degrees of freedom in the phase space. This is like a space-time condition because this is a time. This involves a time integral. So although um, this boundary condition might look consistent with, for example, having a smooth Euclidean vacuum and all those arguments, but from the phase space point of view, this is not very satisfactory. So we kind of failed to come up with like a pure phase space path integral derivation of the entropy of the horizon. But this is still something that we can explore more. So let me just end with final remarks. The path integral in the Euclidean form is tricky. We can avoid some of those issues, but some puzzles still remain. Lorentzian configurations are important, can be utilized in order to approximate the almost real-time path integrals that we came up with. But in order to actually write down those configuration space path integrals over Lorentzian spacetimes, we need to do a lapse contour deformation in order to allow the interchange of the order of the momentum and lapse integrals. And I would think that the phase space path integral is still the more fundamental object and should be explored more. And with that, I thank you for your attention, and if there's any question or comments, I would like to hear. Thank you.
Thank you, Batoul, for a very nice talk, and
Thank you.
it was wonderful to hear from you. And thanks very much for accepting to give a talk. And I understand it's a little late for you because it might be around 11:30 or this thing. But
Yeah,
so
no,
yeah,
it's good. Thank you.
apologize
Thank you.
for the
No, 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 it's fine. Thank you. Thank you for having me.
So one question, just this thing before this thing. So this third remark that you have mentioned, the lapse contour should be deformed to allow interchange of this thing, momentum, this thing. Now, is it possible to like do this, arrange this kind of momentum interchange possible without and like playing around with the lapse contour?
I believe no, I don't
No,
think
no.
it's possible. Yeah, I think if like immediately if you try to do the momentum integral first,
Yeah.
you hit the essential singularity for the
Mm-hmm.
lapse.
Mm-hmm.
So basically we get something like integral of like integral dn e to the something over n. So
Yeah.
at
Yeah.
n equals 0, you have that essential
There is
singularity.
singularity, right.
And it's important because the original contour of integration for the labs was on the entire real line in order to impose the constraint. So n equals 0 was on that original integral.
Mm.
So you cannot get around it unless you deform that contour slightly away from the 0 and slightly away from the real part. Do the momentum integral first, and then maybe send back like epsilon to 0.
Right.
So we discuss in our paper that this is inevitable in order to make sense of the path integral.
Uh-huh. Uh-huh. I see.
I have a question in the same line.
Mhm.
Yeah.
Hello?
Yes, please.
May I? Yeah, like right from the beginning, can't we define the original integration contour for the lapse by excluding this essential singularity point and based on some physical arguments?
Yeah, what would be that argument?
Like in case, like in cosmology, they say n equals to 0 is like formidable because immediate transitions from one hypersurface to final hypersurface is not a possible like event. Like there should be at least some proper time
Right.
elapsed.
Yeah, but at the same time, you see, in the case of horizons, n equals 0 is actually very crucial because that's exactly where the lapse function vanishes. So at least you need to allow for a path integral. If your goal is to use the path integral to compute the horizon entropy, for example, n equals 0 is actually an active player of the game.
I see. Okay.
Yeah.
One more thing that I wanted to ask. So this in one of the slides you mentioned that there is a delta function, and then you basically were expressing the delta function by basically e power I something like that. That itself, e power I thing, that all itself is also basically requiring regularization of its own in order to basically arrive at a delta function definition. So can you
Yes, that is
please
the right.
maybe just approximate the delta function with some kind of a regularized function where the limit is more smooth, like we can do it like that, for example, like a Gaussian kind of a thing. It just squeezes and peaks out, and then basically you get a delta function in some limit of the parameters. But
Yes, so like a distribution.
right.
Yes, I didn't go through those steps. Like, I'm not sure whether writing the delta function in terms of the distribution would help us answer the question of like essential singularity avoidance. Are you suggesting that maybe if I write the
For example,
delta
suppose
function?
delta of x, if we write it as a Fourier transform, e power I k.
Right.
Like
Yes.
we also add some kind of convergent factor in the
Yes.
epsilon times x square, so that it converges basically at the two endpoints. And then in the limit epsilon going to 0, it gives you a delta function basically. Yeah, so like that kind of a thing. So instead of just adding ikx,
Yeah.
I'll add
Yes.
also
Yes.
like
Yes.
minus epsilon x square.
Right.
Epsilon is positive, so when you do the integral, basically epsilon 0 limit, it just gives you a delta function.
Right. Yeah, I haven't explicitly done it that way, but I suspect that we still need to deal with this contour deformation even after that. Yeah.
Yeah, I see.
But I need to do it more carefully in order to be able to say a more precise
Okay,
thing.
okay. Yeah.
Yeah, thanks for the comment.
So let's see if there are any further questions. So as of now, I don't see any raise hands or chat this thing. Nothing except this thing. So any further question from the audience? So it seems like not. So if not, maybe let's conclude the session. And thanks to Batoul very much for the
Thank
wonderful talk.
you.
I think it's
Thank
really
you very much.
interesting. The talk was very cleanly done,
Thanks.
and the points was like very cleanly put up, and it is like really beautiful talk. So thank you, Bataul,
Thank you
for
very much.
accepting the this thing and coming, giving the nice talk too. Okay.
Thank you very much for invitation.
So we'll put it up in the YouTube channel soon, and yeah, we'll share the link also. Okay.
Thank you.
Bye bye.
Thank you, everybody. Bye.